Thanks. Okay, so magnetic note repeat. Let's start. So first about me, a couple of words about me. I'm a software developer. I've been programming since I was 12 years old. My first experience programming was from playing the game Strike Commander, and I was like, these 3D graphics are really cool. How do I replicate that? So I bought the book 3D Graphics by, I think, Alan Watt. And I didn't stop until I had a cube rotating, and then it seg-faulted. But whatever, it was a lot of fun. So I'm also a musician, right? Also around the age of 12, I started playing in bands. I've been mixing the two always, you know what I mean? I've always been trying out technology. I got a 4-track recorder when I was 13 or 14 after I went to Minnesota. And yeah, I've been sort of in college, I started playing around with ESI 32 sampler and Cubase back when it was still only MIDI. And sort of, that's the kind of thing I've been doing. As has been said before, I then sort of studied mathematics and computer science and worked at sort of Goldman Sachs and then sort of a hedge fund for a few years. And then I moved to Berlin to play in some bands. And sort of that led me to what happened there was I was playing in a 5-piece band, and suddenly the 5-piece band went to a 2-piece band. So it went from me playing bass and vocals to me playing bass, vocals, guitar, keyboard, everything, and a drummer. And so basically that sort of led me to this idea for Zen Audio, which has been in development since 2013. And basically it's a DAW designed specifically for live use. Now I know everyone's thinking, yeah, that already exists. It's called Ableton Live. And I say, no, actually, Ableton Live is a great product, but I think there's certain things about sort of playing live that it doesn't necessarily cover as well as it could. Specifically, Zen Audio has first-class support for looping. And what I mean by that is it's kind of a fusion between a looper and a DAW, in the sense that just like a looper, you're going to record material on the live, quasi-live, and have it play back. But unlike a looper, you don't need to trigger it manually. It's triggered by an arrangement which you specify beforehand. So you trade flexibility in that you can't improvise an arrangement, but what you gain from that is sort of the ergonomics are just much better because you don't need to worry about, you don't need to stress out about pressing pedals and stuff like that, right? So the idea is you focus just on your performance and then you can be Zen, okay? So yeah, it's currently in beta. I plan to release it in December for Christmas. And so this talk is about magnetic note repeat, which is Zen Audio ALK's version of an arpeggiator. Okay, it's not really an arpeggiator. At some point I'll add that functionality, but right now it's just a note repeat. And you can get the software at http Zen Audio. Okay, so now let's talk about XMAs a little bit, right? XMAs, it's nice, it's late, it's Friday, and XMAs are pretty simple, so I think you guys shouldn't have any problem understanding this, okay? So XMAs stand for exponentially weighted moving average, and they're also known as EMAs and EMAs, with a W. So let's give it a little bit of context. What is it we're talking about here? Why would you even want to apply an XMA? So you apply it to a time series to get estimates for the next value of your time series. And so a time series is simply a list of values that are generated by the same underlying process. And usually the x-axis is considered time. That's why it's called a time series. Okay? So exponentially weighted moving average. Let's parse that whole phrase, and we'll start with the simplest part of it, the average, right? A simple average is basically called a summary statistic, right, in the literature. If you assume, right, this IID thing here means independent and identically distributed ZT, which is assumed to be distributed normally with mean mu and standard deviation sigma, well then your best estimate for the next value is simply the average. So what I'm saying here, and this is sort of there's a little bit of philosophy in this, which is in the same way as assembly programmers are encouraged to select the operation or the instruction that has the lowest power. So for example, if you're going to do some division by a power of 2, don't use division, instead just do a bit shift to the right, right? In the same way, if you're looking at sort of statistics, don't go and grab a Kalman filter or machine learning if all you've got is a white noise process. Then all you need to use is a simple average, right? And that's called a white noise process, right? So, I mean, granted, it's not used very often, but we're going to sort of increase the complexity. So, next thing is a moving average, right? So the average takes the sum over the entire series, whereas a moving average basically defines a subset, right? It's the sum over, or it's a statistic over a subset of the series, right? And so it's a point estimate, and essentially you define what's called a window, okay? And the window has a size m, whereas the entire data series is assumed to have a size n. And so what happens is that at each point you can estimate the next guy, yeah, the next value of the series, and you just move your window along consecutively. So real simple, right? So a simple moving average does the simplest thing possible, which is it takes that window and it does a simple average over that window, right? So the nice thing is there's a shortcut to reuse the previous estimate. So you don't actually have to do this order m operation at each step. And actually looking at this, there's a mistake here because actually like I should be subtracting xt minus m minus 1. So actually I should be throwing out the last value, otherwise I'm adding to my window, right? Like, so I should be thrown. So sorry about that, that's a bit of a mistake. But the key thing is that you don't need to do an order m operation in order to update your statistic at each point. You can just add like a single value to it, or two values in the case of dropping off the last one. So the shortcomings are that it gives too much weight to the old values, and it doesn't give enough weight to the new values, right? Like, so often, so for example, in finance, you know, simple moving averages are not really used that much because you have this sort of dilemma of like, if I use too long of a series, then basically it's too smooth, the curve, and you don't really catch, like you often use it like, if the stock passes through this moving average, that's a signal to buy or sell, right? And you don't want it to use too long a value, but at the same time, if you use too short of a series, then it moves around everywhere and it's a little bit crazy. You want something that gives more weight to the front ones, but still keeps the longer window, right? And so another problem is that once a sample falls out of the window, it is suddenly ignored, right? So this can be significant if like that value was pretty large, then suddenly you can find your XMA, your simple moving average is moving by quite a lot, okay? So what's a weighted moving average? So that's the next step up the complexity, right? And all we do is instead of putting a weight of 1 in front of each guy in the summation, we put a WI, right? So then the next obvious question is how do we choose those weights, right? And so there's actually an infinite number of ways you can choose the weights. You can choose whatever you want for the weights. And that's kind of a problem. We don't like having to choose weights. We want things to come out intuitively and simply, right? And then there's another problem with this approach, which is that if you have an arbitrary set of weights, then now we are hosed because now we are running an ONM, well, over the whole series, or order m at each update step, right? That's definitely not something that we want. You don't want that in a tight audio loop, for example. Oh dear. Okay, sorry about that. Well, that's supposed to show the exponential weights. So basically, now we come finally to the exponentially weighted moving average. So basically, it's exactly what we had before, the weighted moving average, except let's define a lambda, and let's fix it to be between 0 and 1. And what we're going to do is just say the weights, the ith weight is equal to the ith power of lambda, right? Or lambda to the power of I, okay? And there's this 1 minus lambda term in the front, and that's sort of like, it's kind of like an integrating constant, if you will, okay? So it's a weighted sum. There are weights, so there's nothing new here, actually. But what is a little bit different is that the window is now infinitely long, actually. So that's already like, we need something special, right? Because we definitely don't want to be calculating this the naive way, because otherwise we're going to go right to the beginning of our series, right? Assuming our series is not infinitely long. So lambda is called the persistence. And in fact, like, sometimes if you probably Google this, you'll probably find that they talk about the decay, Well, the decay is simply 1 minus the persistence. So it's pretty simple, right? Like, you just flip those around. I did it like this so that well, I mean, you can do it however you want. It doesn't really matter. And so this is morally what an exponentially weighting movement average calculates, okay? But that's not the way we calculate it. Instead, we use this update formula, right? Which is pretty cool because only 2 variables are needed, like, to calculate it, right? We need the current value of the random process, so that's the input, and the last value of the XMA, right? That was the last output, right? And so, right, so that's the formula. It's pretty simple, right? Nothing special here. Okay, and let me just say that this xt can be a lot of different things, right? It doesn't necessarily need to be a time signal. It can actually even be a sort of power signal, which it can be a signal squared. So for example, like risk metrics, I don't know if you guys have heard of like value at risk. So in the financial industry, you sort of estimate like to a 95% confidence, you know, what is the movement of a portfolio, right? What is the biggest move in a portfolio, right? And so for that, you need to plug in things like volatility, right? Like, and so for that, they just use an XMA of the volatility over the last, you know, sort of 30 days, right, or 25 days. I can't remember what it was. So, you know, it can actually be used for a lot of different things. So why does this work? Well, a better question is actually when does it work? And the answer to that gets a little bit esoteric. It's when the underlying statistical process is composed of a random walk plus a white noise, and they have to be independent. That's not something that I wrote there. So the white noise process is xt equals xt minus 1 plus epsilon t, for epsilon t normally distributed, right? And the white noise is just very simple. It's just Gaussian noise, right? Like, does anyone know what the best estimate for xt plus 1 given, right, for white noise for a random walk is? Right? Let's say I have the random walk on day t. What's the best guess for day t plus 1?
Same as previous?
Exactly. Yeah, that's right. And so actually, that intuition should come into like the EMA, right? Because if you think about it, an XMA is kind of like this random walk, but then you've also got this extra process of white noise, right? And so when doesn't it work? So when the time series in question has a trend, for example, and for that you use a double exponential, which is actually pretty simple. It's just an exponential of an exponential, right? Or I should say an XMA of an XMA. That's why it's called double, right? And so one of the XMAs, there's going to be 2 parameters. Rather than just lambda, you're going to have lambda and let's say kappa or something like that. And basically, one of those is going to try to estimate what the slope is, and the other one is going to continue estimating what the movement around that is, right? And so when there's seasonality in the time series, you use a triple exponential. And if the input, so that's kind of covered, right? If the input has jumps, you're kind of hosed. Then you're in a different territory and you need different techniques to study things. It actually gets a lot more complicated. And also when the white noise components are not independent or have changing variances, which is called heteroskedasticity. And for that, like, there's models like, so for finance, there's option models called the Heston model, where the variance is assumed to itself be a Gaussian process, right? And I think the equivalent in terms of in discrete time is called Garch, right? In fact, heteroskedasticity appears in the world. But let's be practical here and just think as developers, am I really bothered about this? And the answer is, in most practical cases, it doesn't really matter. And I think when we go a little bit further, you'll understand why. Because I consider this is like a basic sort of Swiss Army knife which can be used in tons of situations. And so practical usage, how do we determine lambda? A high lambda is high persistence or low decay, and that is a long averaging window. A low lambda is low persistence or a high decay, which is a very short averaging window. So you can just choose a low value and a high value and then start bisecting and then like literally run it until you get the desired result. So this is really not rocket science, okay? One thing to watch out for is denormaling floating point calculations, right? So if you get very close to 0, you just want to clamp it to 0, right? So here are some code examples. This is how it appears in my own code base, right? Like, so for example, the smooth level, the first guy here, is just how I calculate the meter for the audio, right? Like you see a meter appearing and you don't want it to just drop right away. So that's why there's this input level times input level. And at some point later, it'll be square rooted, right? And then the second one is the animate camera. And I just wanted to point out the animate camera, right? Because for two reasons. Firstly, because if you see here the 1 minus a and the a, right? This is like just, you see I just hard coded it in, right? Like it works well enough. Like, so the two things are basically, first of all, those zoom factors and the center position and stuff, those are vectors, actually. Those are GLM vectors. So basically, you can just run this on vectors. And the nice thing about C++ is you've got this operator overloading. So basically, you just plug it in. It's exactly the same equation, right? Second thing is when t gets close to 0, right? That's that second if statement. Then I just clamp everything to 0.
Well, why are you squaring the input level just to avoid the negative?
No, because you want the root mean square, right? Like otherwise, like you can also take the absolute value of it, right? Like, but you want to make like otherwise you're going to get negative values for that, right? Yeah. So basically, that takes us to magnetic note repeat, which is kind of a quasi application of this XMA stuff. And basically, here's what it is, right? In other arpeggiators or note repeat effects, you basically have two modes, right? And it's either mono or latch. You know, this is like, well, I've got F expansion strobe here, and I don't want to pick on F expansion strobe. I think it's a great like sort of VST. That's right. You guys just got bought by Rolly, right? Like, well, I don't know you guys, but and song or beat when you hold down a key. So basically, yeah. So latch is basically you get immediate feedback, right? You hit the note and you hear it right away. But you know, if you made a mistake, you're kind of host, right? It's going to repeat that mistake ad infinitum, right? So, and the second one is beat, which is much better, right? It's usually what you want, right? The problem is when you hit that note and you hit it early, it's not going to give you instant feedback, which is sometimes kind of just weird, right? And if you hit it too late, then it's even worse because then, so for example, you're supposed to hit this big chord on the chorus, and actually, you know, it's actually like an eighth note late, you know. So that's not so cool. I think we can do better, and that's what I tried to do with magnetic note repeat. So the fundamental idea here is just treat the errors in timing as a like sort of statistical signal in its own right. So basically, when you hit a note, there is an error with respect to the closest grid point, and we're just going to decay that error over time. So what that's going to do is just going to slot it slowly into time. And so, you know, here I've got the equations for it. It's not really that important that you understand it. So this epsilon is the difference between the t onset, so basically the time that you actually hit it, and the quantized time. And so basically, we're going to update that t onset. So we're going to move it to the next point by taking the quantized position plus the change, right? Like, so that will be depending on whether it's an eighth note repeat, a quarter note repeat. And then we're just going to add that epsilon to it, but we're going to multiply it by 1 minus our speed. And that's going to be taking care of our decay, right? So the speed controls how fast we revert to the musical grid. If we have a speed of 0, that's basically a latch mode, right? So, and if we've got a speed of 1, that's our beat mode, because basically we correct that error immediately within one go. And between 0 and 1, we have like something in between. It sort of slowly comes back in. So that's nice because we've turned a switch into a dial. So, you know, I kind of like this idea of taking something which is bimodal and turning it into something that's like something can vary continuously. So that's it. Then now I'm going to give you guys a demo. Let's hope this works. And now you guys get to see my rockin' guitar. So, I mean, like, I'll be honest with you, this is not the most amazing set song. This is Zen Audio, by the way, and it seems that like this HDMI thing has done something weird with my settings. So, wait, am I not? Yeah, and so what I've done here is I've set it like quite slow because that way you can really hear the effect. Otherwise, you just hear it slowly coming into power in time, and it just sounds right. Okay. So, let's go here. Let's start. Okay, so basically now I'll go up here to chromophone and put the note repeat on. Let's put it to 1/4. So okay, and now, so what I'm going to do now is I'm going to draw some automation. Well, let's just loop over this bit. And so basically here, I'm going to set this to be chromophone's speed. And the same thing here. Same here. Oops. All right, now what I'm going to do is just going to switch this to curve mode. This one as well, this one as well. And so I've got this one now all the way down, right? And this guy like that. So, well, no, let's just leave it like that. And this guy, I'm going to play around with it a little bit. I'm going to do a little curve like that. OK, so basically now I'm going to go through here. And what I'm going to do is I'm just going to play my note a little bit off. It will be difficult for me because my timing is amazing, but I will try. And so then what you should hear is like just in this first one, you should hear it like not coming back. You should hear the latch mode. In the second one, you should hear the beat mode. And in the last one, it'll start varying between the two. So here you can hear it right back. So yeah, oh shit. Sorry. Anyways, that's it actually. Look at the time.